So let's look at force time graphs. So a force versus time graph can tell us an object's impulse. So the area under a force time graph tells us the impulse. So we have F times delta T equals J, which is the impulse. For our force here, if we look at this graph, so we have force on the y-axis and time on the x-axis. So we have force is at 20 newtons and time is at 5 seconds. So we have force of 20 newtons, time of 5 seconds. So if we're looking at the area under here, we have area is equal to base times height. So that's equal to, the base is 5 seconds, the height is 20 newtons, so we have 20 newtons times 5 seconds, and that equals 100 newtons seconds, which is equivalent to 100 kilogram meters per second. All right, now we have a change of momentum is equal to the final momentum minus the initial momentum. We're assuming that our initial velocity is equal to 0 meters per second. We have a mass of 5 kilograms, and we want to figure out the final velocity. So our impulse is 100 kilogram meters per second. So our impulse, remember, right down here. So impulse is equal to the change of momentum, which is equal to mass times change of velocity. So we have 100 kilogram meters per second, which is equal to our mass, which is 5 kilograms, times we have our final velocity minus our initial velocity of 0 meters per second. So if we divide both sides by 5 kilograms, let's get this up here, we end up with 20 meters per second equals our final velocity. All right, so what if the force isn't constant? So in the last graph, we saw a constant force, just a graph with a big rectangle. So in this situation, we've got a weighted ball dropping onto a force sensor. So the ball drops, hits the force sensor, and then rebounds up. So we have a starting height for the ball at 1 meter. And then when the ball hits the force sensor and rebounds up, it rebounds to a height of 0.35 meters. So the question is, does the area of a frequency or a force versus time graph still equal the change in momentum if the force isn't constant? And the answer is yes, and we're going to show how that's true. So we want to calculate the velocity before the collision, and then we want to calculate the velocity after the collision. So since the ball starts at rest, our initial velocity in the y direction is 0. Okay, so we have, and we know acceleration. This is acceleration in the y-axis, so it's just g. So we have vy squared equals 0 plus 2 times, we'll use 9.8 here, 9.8 meters per second squared, times we have 0 minus 1.0 meters. So if we do some simplification here, so 2 times 9.8 times negative 1 is going to be, so vy squared is equal to minus 19.6 meters squared per second squared. So if we do the square root on both sides, we end up with vy is equal to minus 4.43 meters per second. So the ball is falling at a rate of 4.43 meters per second. All right, now we want to figure out the velocity after the collision. So after the ball hits the ground, or after the ball hits the force sensor and bounces back up. So we know now that our velocity when it hits the ground is 0. So again, this is 0. Our acceleration is still 9.8. Our initial y position is 0, and our final y position is going to be the 0.35 meters. All right, so we have Vy squared equals 0 plus 2 times 9.8 meters per second squared times 0.35 meters. All right, so we have Vy squared equals 6.86 meters squared per second squared. If we take the square root of that, we have Vy is equal to 2.62 meters per second. So the velocity of the ball as it's dropping is minus 4.43 meters per second, and the velocity of the ball after it hits the force sensor and is rebounding back up is 2.62 meters per second. Okay, so here on the right side we have the graph from the force sensor. You can see this. You can see this here is the graph from the force sensor. So we're going to use the information provided to determine the change in momentum. So delta P. So delta P, remember, is equal to mass times delta V. All right, so our mass, so delta P then, is equal to 0.43 kilograms times our delta V is the final velocity. So that's 2.62 meters per second minus 4.43 meters per second. So that ends up with a delta P of 3.03 kilogram meters per second. Okay, so now we're going to estimate the area under the force versus time graph here. And we're going to do that by using the area formula. And we want to know what area formula to use here. And we're going to do that by figuring out what the shape of the area under here looks like. So this looks like a triangle. So the area of a triangle equation is 1/2 base times height. So our height here is 300 newtons. Our base, if we look here, is about, so the base is about 0.022 seconds. So we could say it's about, so the final point here is at about 2.097. So that's that point right there. And this point here is at about 2.075 or so. So subtract those from each other and you get 0.022. So to figure out our area under the graph, we're going to do area is equal to 1/2 times our base, which is 0.022 seconds, times height, which is 300 newtons. Multiply that together, and we end up with 3.3 Newton seconds, which is equal to 3.3 kilogram meters per second, which if you compare to the answer that we got by doing by looking at our calculations, we had an amount which was 3.03 kilogram meters per second. So the difference here is about 0.27 kilogram meters per second. And then finally here's the area that's calculated by an integral. So this is the force versus time graph that we were looking at before. So force versus time graph that we were looking at before, that came from the force sensor. So this is from the force sensor. And the integral calculated this. You can't see it very well, but it's 3.29 Newton seconds, or 3.29 kilogram meters per second. So if you compare that to the area that we calculated using the area formula, we got 3.3 kilogram meters per second using our area. So area is equal to 3.3, so that's very close. And then our the amount that we calculated using the velocity numbers was 3.03 kilograms meters per second. So this was using velocity. So our percent error between the calculations we did using the velocity and the calculations you did using the area formula and the integral is about 8%. Not too bad.